A 1-gigawatt AI data center can consume as much electricity in a year as 730,000 American homes. The bet is that machines drawing this power might help us invent a better energy system. They could control fusion plasma, discover new materials, make grids more efficient, and reduce emissions across industry. So we are using energy to build a tool that might transform energy. Can AI create more clean energy value than it consumes? We need an accounting test. The cost side includes electricity, backup generation, construction, chips, water, and associated emissions. The benefit side includes measured energy savings, additional clean electricity, avoided emissions, and deployed scientific work. A predicted molecule is not a commercial battery. A controlled plasma experiment is not a fusion power station, and an efficiency estimate is not an avoided ton of carbon. We will count demonstrated results, label modeled possibilities, and separate future breakthroughs. The International Energy Agency says data centers consumed about 415 terawatt-hours globally in 2024. It expects consumption to more than double by 2030, with AI as the main driver of growth. Half of the additional supply through 2035 is expected to come from renewables, but natural gas and nuclear generation also expand. That makes AI an infrastructure industry. Money flows from subscriptions into chips, buildings, cooling, substations, transmission, power plants, fuel contracts, and finance. The climate result depends on what generation is actually built, where it connects, and when it operates. The Moonshots investor panel describes the bottleneck directly.
The compute supply chain is caught up, but the energy constraint hasn't. The energy supply hasn't. And so what we're living through right now is this frenzy for energy contracts where compute providers are trying to outbid each other to buy literally just energy supply.
Fusion will not power the data centers being connected today. In the near term, new demand can support solar, wind, batteries, restarted nuclear units, and new natural gas generation. The IEA estimates electricity-related data center emissions at about 180 million tons of carbon dioxide today. Its base case reaches 300 million tons by 2035. Globally, that remains a small share of energy emissions. Locally, however, concentrated demand can determine whether a plant stays open, a gas project is built, or transmission capacity goes somewhere else. AI's future benefit does not erase this near-term choice. The optimistic case is that AI can reason through physical systems humans struggle to visualize.
So in parallel with that, you've got things like magnetic containment of a fusion reaction, very hard to visualize. AI just cuts right through it.
There is real evidence behind part of that claim. In 2022, DeepMind and the Swiss Plasma Center used reinforcement learning to control 19 magnetic coils on a research tokamak. The controller shaped plasma into several configurations and operated directly on the machine after training and simulation. In separate work at the DIIID facility, researchers used deep reinforcement learning to avoid tearing instabilities. The system combined hundreds of sensor inputs and adjusted magnetic confinement in real time. These are difficult, physical demonstrations, but neither experiment generated commercial electricity. AI addressed control problems inside a much larger system that still needs suitable materials: heat removal, fuel handling, maintenance, regulation, and competitive cost. AI can shorten part of the research loop. It cannot remove the rest of the reactor. The larger, near-term opportunity may be less spectacular. AI can forecast renewable output, detect methane leaks, optimize industrial processes, manage buildings, and find unused capacity in transmission networks. In a widespread adoption scenario, the IEA estimates existing AI applications could reduce emissions by 1.4 billion tons in 2035. That is several times its projected data center emissions. It also estimates AI could unlock up to 175 gigawatts of additional capacity from existing transmission lines. These are modeled possibilities, not a measured global balance. They depend on sensors, access to operational data, equipment upgrades, skilled operators, regulation, and companies choosing to deploy the systems. Scientific discovery is only the first economy. After an AI proposes a material or control strategy, laboratories must reproduce it. Engineers must build it, factories must manufacture it, regulators must approve it, customers must finance it. Energy technologies often take decades to move from discovery to widespread use. The IEA notes that commercialization can be a larger obstacle than invention. This is the hidden economy behind AI solving climate change. Compute may make searching cheaper, while testing, factories, grids, permits, and construction remain stubbornly physical. The useful question is not whether AI produces an exciting answer. It is whether the complete system reaches deployment sooner. Meanwhile, someone still pays for the power system AI needs today.
Just force the data centers to create their own power and you're done. It's just that easy.
Or pay a differential rate and just have the data centers pay a higher rate that actually drops the rate for everybody else.
The principle is reasonable. The implementation requires more than a promise. A data center should pay for the generation and wires it causes. It should keep paying if its project is delayed or uses less electricity than contracted. Its clean power claim should identify the location, operating hours, and additional generation involved. And if the facility offers flexible demand during grid stress, that performance should be measured and penalized when it fails. Virginia has already created a separate rate class for very large customers, including minimum payments and longer contracts. These rules do not decide whether AI is worth building. They prevent existing customers from financing the experiment without seeing its costs. Now we can define success. For every major AI campus, publish committed load, actual electricity use, hourly generation, water consumption, and electricity-related emissions. For every claimed climate application, publish the baseline, measured intervention, energy saved, emissions avoided, and whether the result survived independent physical validation. Scientific projects should also report whether AI reduced experiments, cost, or development time, not merely how many candidates it generated. This creates a climate return on compute. Fusion control belongs in the measured results column. Commercial fusion electricity does not. Projected global savings belong in the modeled column until deployment turns them into observations. Okay, so what does this tell us? AI may become an important climate tool. It is already controlling plasma experiments and operating parts of the energy system. But it is not a substitute for clean generation, factories, transmission, or climate policy. The next step is one auditable gigawatt scale test that reports both sides of the ledger. Every unit of energy consumed today and every independently verified climate benefit produced. If we are going to spend a gigawatt trying to reinvent energy, we should know exactly what comes back.